Hello everyone, I'm Jingru Mo from the Department of Electrical and Computer Engineering in the University of Florida, and this is my course project presentation for EEL 6509, Wireless Communications. The name of my project is Rake Receiver Simulator Design and Analysis in CDMA System. The presentation will be in two videos. This is the first one. The presentation includes two parts. The first part is to introduce the topic and a description of work I did. The second part is the demonstration of the simulator interface. In part 1, first I will describe the rake receiver under study, the reason why this kind of receiver is useful in CDMA system. Secondly, I will show you the design of each part of the simulator and present the results of one experiment to illustrate the performance. Thirdly, several design approaches of rake receiver will be introduced. Finally, I will draw a concise conclusion to part 1. In part 2, I will first conduct some experiments on the simulator to show you how it works, and then show you each part of the code of the simulator. First, in wireless environment, reflection and scattering can cause multipath effects, and the multipath effect can significantly degrade the performance of communication systems. Hence, we need some techniques to overcome or even utilize this effect. Rake receiver is one of the applications of such technique. That is, what is rake receiver? A rake receiver is designed for CDMA system. It provides diversity by means of using multiple matched filters. Each branch or finger of the receiver has a matched filter, and it can detect one multipath component. After collecting and detecting a certain number of multipath components, they can be weighted and combined to produce a better performance of decoding in terms of bit error rate. Why do we use rake receivers in CDMA systems? First, CDMA system uses a wideband, typically 1.25 MHz, and so the chip rate is very high. Wideband system may suffer from intersymbol interference, but CDMA systems use orthogonal codes, for example the wash code. Moreover, the information bits are spread by the long orthogonal code. Hence, the correlation between adjacent chips is very low, so we do not use equalizer in CDMA system. Secondly, in wireless environment, the multipath effect leads to different propagation delays. Thus, the receiver can receive multiple copies of the signal, and these copies can be considered as uncorrelated, so they can be separated. Thirdly, since every user in CDMA systems use the same frequency at the same time, hence, in order to control the interface, the transmitting power need to be strictly controlled. If the receiver can provide diversity combining, the sum of the energy in multipath components is larger than that in one component. Thus, diversity combining can improve the signal-to-noise ratio, which directly affects the bit error rate. There are several motivations of this work. First, I want to design a simplified multi-user CDMA transmitter and a simple rake receiver in MATLAB GUI. This interface can be manipulated by people to conduct different experiments. Secondly, I want to conduct experiments to see the effects of the number of fingers in use in rake receiver. Thirdly, I want to see the performance in different channel conditions. For example, the channel only with white Gaussian noise and the channel with white Gaussian noise and the Rayleigh fading. Finally, I want to learn the different approaches of rake receivers and analyze their performances. Next, I will introduce the design of the simulator. First, the overall interface of the simulator is shown in this figure. The interface itself includes 4 parts basically. The first panel here, you can set the parameters here. Note that the first one, the length of wash code, the number you put into here is 2 to the power of this number. For example, if you input 5 here, the wash code will be 2 to the power of 5, that is 32. We can also set the number of users, the number of information bits sent by each user, and the signal-to-noise ratio, and the number of fingers in the receiver. After setting all these parameters in the first panel, the second panel will output the performance of the system in terms of bit error rate and bandwidth efficiency. At the same time, the third panel will also present the corresponding coefficients of the receiver. The first 3 added boxes will present the number of delayed chips detected by each finger, and the next 3 boxes will present the weighting coefficients of each finger. The methods of calculating such coefficients will be explained later. Here I start with the transmission part. According to the value you input into the first panel, the wash function matrix is generated. The code of generating wash code is in wash.m file. The first wash function will be assigned to pilot signal, which is important in channel estimating. The rest of the codes will be assigned to users in the system. Then, again, according to the number of the first panel, information sequences of each user will be randomly generated. Here we assume that every user wants to send equal length packets. The modulation scheme is BPSK because BPSK can provide the best energy efficiency. Under the constraint of low power level, energy efficient modulation scheme can give lower bit error rate. Then in this project, we consider 2 kinds of channels. First, the first kind of channel only introduces additive white Gaussian noise. Then the received signal can be expressed by this equation. The xt is the transmitted signal and nt is the noise. Note that the SNR can be set in the interface. The corresponding noise will be added to the channel. Another type of channel is Rayleigh fading channel. Of course, the white noise is also there, not changed. In this simulator, slow fading is assumed. That is to say, the Doppler frequency is assumed to be relatively small. Then the received signal yt can be expressed like this. The magnitude of ht is a Rayleigh random variable, and the square of it is exponential random variable. At the receiver side, channel estimation is needed because the receiver needs to use the pilot sequence to estimate the delays of each multipath component and the weighting coefficients of each finger, so that the diversity combining can be achieved. First, estimate the delays. Because the pilot signal and the corresponding wash code is known at the receiver, and the multipath components are also orthogonal to each other. Hence, we can shift the received signal and correlate it with the wash code. Every time the received signal is shifted by one chip, and conduct the correlation. If there exists significant peaks, the number of shifted chips is the delay of this component. Because of the orthogonality, the peaks will exist only when the signal is delayed by the right number of chips. After deciding the delays, we can estimate the weighting coefficients. The receiver uses the output of each correlator in each finger to calculate the pilot signal power. Then the values of the pilot signal power are normalized to get the weighting coefficients to each branch. The normalization formula is presented in the report. Here is the overall model for the receiver. After channel estimation, the tau and alpha are specified. The tau are the delays of each finger and alphas are weighting coefficients. Each alpha is multiplied to the output of the correlator. Then the outputs of each finger are combined together. Then the combined signal is input to the demodulator. Because the received signal by because the receiver has the knowledge of each user's wash function, coherent demodulation is used here. Then the decision device is used to make decisions. We use maximum likelihood decision rule. Because the transmitter uses BPSK, hence the threshold of the ML demodulator is 0. Positive numbers are mapped to 1 and negative numbers are mapped to -1. Finally, it converts all the -1 to 0. Thus, the information bits are recovered. Here we will analyze the performance in terms of bit error rate and bandwidth efficiency. First, the bit error rate is the ratio of number of bits in error and the number of total information bits. Typically, the bit error rate is determined by the signal-to-noise ratio, since the choice of fingers can affect the diversity. Thus, it can also affect the signal-to-noise ratio. So, as we will see later, typically the more fingers we use in the receiver, the better performance of the BER. Next, the bandwidth efficiency is bit per second per hertz, and this formula used here is to calculate the bandwidth efficiency. In CDMA system, all the codes are orthogonal, hence the dimensionality is equal to the number of different codes, and it is also equal to the length of the wash code. In order to see the relationship between SNR and BER using different number of fingers, you can use the plot function of the simulator to plot the curve. In order to get reasonable experimental results, I set the length of the information bits to 100,000, and the simulator calculates 6 bit error rate values corresponding to 6 values of signal-to-noise ratio, that is from 5 dB to 10 dB. Thus, I use the best fit curve to fit these points to get the curve. The fitting method is MMSE. Note that changing the number of fingers can significantly affect the slope of the curve. Additionally, the performance is better in AWGN channel than that in the fading channel. I will give an example later in the demonstration. Here I captured 2 figures of the simulation results. Both of the plots are from the 3 fingers receiver. The first one is the bit error rate curve in AWGN channel. We can see that the BER is dropping quickly as the SNR increases. In the second plot, the channel includes Doppler shift. The Doppler shift frequency is set to 10 Hz. As we can see in the plot, the bit error rate is significantly larger than the previous one. Moreover, the curve is more like a linear line. When the SNR is larger than 10 dB, the BER is still larger than 10 to the -2. However, in the first plot, when the SNR is larger than 10 dB, the BER drops below 10 to the -4. Later, I will demonstrate the performance of the receiver in which less fingers are used. That's all for the first video. The next part will be in video 2.